Assalamu alaikum everyone. Welcome to the project presentation of Group 4. I am Abdullah Mahmood, ID 1706010. My other group members are 08, 17, 20 and 33. Our project is 8-bit arithmetic and logic unit. Here the system will take two 8-bit numbers as input and will perform various operations on them. Here is our arithmetic block and here is our logic block. Now if we go to the child sheet of our arithmetic block, here different blocks are performing different operations. At first, this is our adder block. It is taking two 8-bit numbers as input. Now if we go inside, here we can see eight full adder circuit. If we go also inside it, now these blocks are composed by primitive gates. So this is how our adder block is working. And now this is our subtractor block. It is also taking two inputs. Now in its child sheet, here we can also see 8-bit adder, but it is working as 2's complement. So there is a NOT gate, and inside these blocks there is also a circuit composed by primitive gates. Now this is our increment block. It is taking only one number, as increment operation can be done at only a one number at a time. Now in its child sheet, here two 4-bit full adders are used, and one is added to the LSB of the number, so it is incrementing the number by 1. And finally, this is our decrement block. It is also taking one number, as decrement operation can be done at a one number at a time. And in its child sheet, it is decrementing the input number by 1. So this is our circuit used here. Now if we want to see some examples, so there are two numbers A and B, and we can give the input here. This is our element of A and this is the element of B. The switching sequence are giving here. Let's say we want to do addition, so the sequence is 0 0 0 0. If we give the sequence here, switching signal, and run the circuit, here the output is given 202, which is the sum. Now if we want to do subtraction, which means 0001, and by changing this, our output is 38, which is the difference between these two. Our circuit works in such a way that A has to be greater than B, as we are subtracting B from A. So this is our output. And for incrementation, code is 0001. So it is incrementing 120 by 1, so the output is 121. And for decrementation, it is given a result 119. So this is how our arithmetic parts are working.
Now I will explain the multiplication block. Here on the screen you can see that 16 and 15 are multiplied to get 240. Switching signals 0, 1, 0, 0 gives the multiplication output. If we see the basic technique of multiplication, for a 4-bit number, this is the basic logic of multiplication. We can see that the LSB of each partial product is directly given to the output. Then the next bit is multiplied with all the bits of the previous number and added except the LSB which went to the output. Thus by adding we get the output. Carry out of the last adder is the MSB of the multiplication. The same logic has been implemented for 8-bit in our circuit. For 8-bit multiplication, 7 adder stages were used. Also, AND gates were used to multiply bit by bit, which can be seen from the circuit. So the carry out of the last adder gives us the MSB of the output number. Thus we get our desired multiplication output.
I will be describing the division part. The divisor B is taken here and it will act as a source subtrahend throughout the whole process. The most significant bit of the dividend is taken at first and is kept in the least significant position. Zeros are added in the higher positions and thus the minuend is constructed. The carry bit of 1 indicates that the subtraction is being performed. After subtraction, the output carry obtained is sent to an XOR circuit with the input carry to obtain a switching value, and this value is inverted to get the most significant bit of the quotient. Next, some marked circuits are implemented to construct the next minuend. If the switching value is 0, the bits from the difference obtained earlier will contribute to the next minuend. Otherwise, the original minuend will contribute to the next minuend. In the subsequent subtractions, the same process of making minuends and subtracting from the subtrahend is followed. However, when the least significant bit of the dividend is taken into account, the output bits from the marks are used to determine the remainder obtained in this process. Now I will show some examples. At first, I am dividing 15 by 4. The quotient and remainder are both seen to be 3 as expected. Now I will show another example where we are dividing 15 by 5. The quotient is now seen to be 3 and there is no remainder as expected. Now I will show yet another example where we are dividing 15 by a larger number 20. As expected, we can see that there is no quotient while the remainder is 15.
Now here we look at the logic unit. We have basically done bitwise operation over two input A and B, which is later controlled by these 4 marks, so that on the basis of the switch selection any of the logic can be performed. Here we can see the first 4 circuit. They contain basic AND or NOT and NAND gates. For a 8-bit input, each gates are placed for 8 times and perform their usual operations. Then we have next 3 operations, which are NOR, XOR and XNOR. As usual, they have 8 gates each too. Finally, we have a comparator which will take 2 separate numbers as input in this unit. Two 4-bit 7485 comparators were used to compare between their LSB and MSB and to give decision about their equality or which one is the larger. Now we'll demonstrate output of some of these operations. For switch 1000, bitwise AND operations will be executed on A and B. Here we can see the input of A and B, and for each bit of A and B, there is AND operation is executed here. Similarly, for switch 1101, XOR operation will be executed. And here, for the same A and B, we can see the execution of XOR. Finally, for the comparator part, here we keep A greater than B, and this portion is presenting the same result here.
Now we will see the switching operation at first. Here we used 4 bits in the switching operation. Last 3 bits goes to the arithmetic and logic unit, and then goes to A and marks IC 74151, and we get an output from Y. The output goes from the arithmetic and logic unit. The output from the arithmetic and logic unit then goes to a 2 to 1 multiplexer. The switching signal is then comes from the 4th bit of the switching sequences that we seen shown earlier. Here you added a switching operation manual for the quick, quick operation. Here we see the input limits. Here A or B both are 8-bit numbers, and 8-bit binary number can represent 255 at most for unsigned integer. So we use 3 7-segment displays to show the binary numbers. Now you see deeply in the conversion method. For conversion, we use 2 EEPROM module, which is IC 2732, which is also known as erasable and programmable read-only memory. It gives the BCD values corresponding to the binary values using its loaded program. Then we use 37447 IC, which converts the BCD numbers into 7-segment display values. Here we can see that the 7-segment display values are connected according to their 100, tens, and unit position respectively. Now we will look into our outputs. Here we use 16 bits in the output. Adding to 8 bits sometimes create an extra carry out bit, which is shown in the 9th bit. Again, multiplying to 8 bits gives 16 bits in total. That's why we use 16 bits at output. Here we use the same conversion algorithm to show the binary to convert the binary to decimal. The division here we need to mention another thing. The division operation has two different outputs. One is quotient, which is shown in the 0 to 7 bit and the corresponding decimal display, and the another is remainder, which is shown in the 8 to 15 bits and shown in the corresponding display. So that's all from our project video. Thanks for your patience.